Here is a complex problem on rotational equilibrium. We have this bar right here, shown in blue. It's resting on this ledge right there, so immediately we know there's an upward normal force from the ledge. It's also suspended by this cable. Cables are like strings. They're like ropes. They have tension forces. So there's a tension force right here. Okay, there is a block hanging from the bar, so it pulls down with its gravity, which is 95 times 9.81 g. But the beam itself, the bar, has its own gravity force, so we have to draw that stemming from the center of the bar. Its mass is 55. Now we've drawn the forces. There is another force. The bar is also getting pushed this way by the wall, but we can leave that out for this problem. To find the tension, we are going to balance the torques. This is an unknown force, but so is Fn. We can't have two unknown forces in our problem. So when we balance torques, one of those forces has to disappear. How do we make it disappear? We say that it acts at the pivot. So I am going to make this my pivot. You could choose any point because the bar is not rotating. The torques, the torques balance at this point because it's not rotating about that point. The torques would balance at this point if I wanted them to, because there's no rotation about that point either. At every single point, there is no rotation around that point, so the torques must balance at every point on the bar. But by choosing this as my pivot, Fn has no torque. It acts at an R of 0 when this is my pivot. So that's really convenient, and it's going to help me find a single unknown, the tension force. Okay, so this force is trying to pull counterclockwise. This one and this one, those try to pull clockwise. So we have to balance the counterclockwise torques with the clockwise torques. We make them all positive. I've got two that are counterclockwise, and I've got one that is clockwise. So let's go blue. The first one I'll do is this guy. So its force is mg, the gravity force. Where does it act? Well, this distance would be half the length, so L over 2. Next, pulling clockwise, or counterclockwise. Oh no, this is clockwise. I've done this wrong. Oops. Let me fix that. This guy pulls clockwise as well, so its force is the gravity force, mg, and it acts, how far is it from the pivot? The full length L. All of it. Then we have tension, the force of tension, pulling counterclockwise, trying to balance those other two torques. Where does it act? It also acts the full length L from the pivot, right? And I've included sine because this does not point at 90 degrees to the position. It points at 14 degrees. You might say, well, what about sine theta here? And shouldn't we have a sine theta here? Yeah, we should. But because the angle is 90, we can ignore it. Sine of 90 is 1, and you do not have to show when you multiply by 1. So look at this. Almost by magic, you can divide both sides by L, and the L's will cancel out. And now you have a single unknown in your equation. So you can solve for force of tension, and hopefully you get this value, roughly. For part B, we know the upward pointing forces must balance the downward pointing forces. So that's 55g, 9.81 there, plus 95 times 9.81. So you can plug in the value here and solve for the unknown. Thanks for watching.